So this video we're going to prove Cauchy's integral formula. So Cauchy's integral formula says the integral f of z over z minus a dz is f evaluated at a over some simply closed contour. So this is kind of a picture of kind of what we mean. So we have the f holomorphic on this simply connected domain U, and we have this simply connected contour C, which we're integrating over, and a point A is inside that contour. As part of this problem, we will need this lemma, which says this integral here, which is basically just this integral, but with A instead, is just f evaluated at A. This is actually way easier than this part. But not way easier, but this just requires you to use Cauchy's deformation theorem to just deform this curve into a circle of radius r around A, and then parameterize it. So I'll leave that as like a homework or something. So what we're going to do is we're going to use the fact that f is analytic, which is the main idea. So f is analytic means it has a derivative. So it has a derivative, which means that given epsilon greater than 0, we can choose delta, and in particular we want delta to be less than 1 and bigger than 0, such that if the absolute value of z minus a is less than delta, then we have that f of z minus f of a over z minus a minus f prime, which is a derivative, evaluated at a, the difference between these two is less than epsilon. So this is the definition of the derivative existing, right? For all epsilon, there is a delta such that, this implies this. So we've chosen a delta, we've chosen it. What we want to do is now calculate this integral, f of z minus f of a over z minus a minus f prime of a dz. And we want it, well, using Cauchy's deformation theorem, we're going to use C of R, but the answer will be the same as if we used C, but R is easier. Okay, so there's something I keep forgetting. In all of these, we need 1 over 2 pi I as a constant 2 pi I, which I keep forgetting. And also here, 1 over 2 pi I. Although in this case, it's not really necessary, but we'll just put it in anyway. We want to show that this entire thing is less than epsilon, and because epsilon, we just chose epsilon to be anything. If we show this is less than epsilon, then, because epsilon was arbitrary, we could choose epsilon as small as we like, and by analysis, then this is just 0. So let's actually take the absolute value of this. This is less than or equal to, well, 1 over 2 pi, which is this front bit, and times by the length of this integral. Length of this integral would be just, this is radius r, and so the circumference is 2 pi r. Then we want the maximum value of the inside, right? So what we're doing is taking the length of the integral and then multiplying by the maximum value of the inside of the integral, which will give you the upper bound for the value of the integral. This is the maximum, actually supremum or something, z minus a, z minus a equals r. So this everything on this circle will be something of this form. Absolute value of f of z minus f of a over z minus a minus f prime of a. Okay, and to upper bound this, we're going to just say, well, because we chose a delta, for which this is true, we're going to just say r is less than delta. So that means this z minus a is less than delta, which means using this we can get this whole thing is less than epsilon, and also r is less than delta. So let's put that together, then we get this 2 pi's cancel. So a lot of things together, but r is less than delta, so we get this delta. Instead of r, we can replace it with delta, and because r is less than delta here as well, using this we get it's less than epsilon. This pi is less than epsilon. And because delta is less than 1, this product is less than epsilon. So this is less than epsilon for every epsilon, which means this whole thing is 0. Hopefully that made sense so far. And so finally, I mean, actually, we're really almost done. So what we have is this whole thing is 0. So let's actually write that out. And we want to split this up into the different pieces. So we have one piece, which is this, f over z minus a, another piece, which is minus f over a, z minus a, and then this piece, f prime of a. That means 0 is equal to integral. Okay, so because we can just interchange this CR with a C, now we're going to put back in the C because we don't need the CR anymore. So again, we're using Cauchy's deformation theorem to go back and forth between the C's and CRs. We're going to forget the dz for a minute because it's a bit annoying. 1 over 2 pi I C f of a, and subtract this as well, minus. And now we want to see what we can do. So we knew this is 0, and that gives us this. What can we do to simplify this? Well, this over here, we're integrating a constant around a loop. So by Cauchy goes out theorem, so Cauchy goes out, it says that any analytic function around a loop will give us 0, and the derivative of f, because f is holomorphic, is also holomorphic, that means analytic on C, and so this thing goes to 0. So that's because it's holomorphic on this entire U. Alright, so what about this other two? Well, actually, for the other two, we don't actually need to worry, because remember, we said earlier with this little homework problem that this f of a bit is just f at a, and so just moving this to the other side, we're actually done. So we get 1 over 2 pi I C f of z over z minus a dz is equal to this, because this is 0, we just have these two left behind, we move this to the side, 1 over 2 pi I f of a over z minus a, and finally this is just f evaluated a, and we're done. That's Cauchy's integral formula. So I hope that made sense. Thanks for watching. See ya.